Welcome to Module 1, Introduction to Materials Science. Let's start by distinguishing materials science from materials engineering. In materials science, we are focused on understanding the fundamental origins of materials properties, for instance, developing theories of physics. In materials engineering, we can use the results from materials science and apply them to develop new materials, processes, and products. Engineering materials can be classified into three main groups according to their composition and structure. Those groups are metals, ceramics, and polymers. We can have materials that actually mix two types of or two classifications of materials, and those are called composites. For example, carbon fiber in an epoxy resin is a mixture of a polymer and a ceramic. In this graph, we can see the development of the usage of materials over time. The vertical height of each section gives an idea of the proportion of the use of the material estimated to be at that time. So if we go back to the Bronze Age, 5000 BC, we'll see there's a small usage of copper, indicating it was still a very special material. And then we see that about 50% is naturally occurring polymers and elastomers in the form of wood, skins, and fibers. And another 50% roughly is ceramics in the form of pottery. As we move through eras of human civilization, we go from the Stone Age, Bronze Age to the Iron Age around 1000 AD. Now, it wasn't really until the late 19th and early 20th century that the important theories of atomic theory, thermodynamics, and quantum theories have been developed. Those theories are crucial for understanding modern materials and forms the basis of modern material science. We can see the usage of metal peaked around 1960. And as time has gone on from that point, we've seen materials such as polymers, elastomers, composites, and ceramics and glasses starting to replace the usage of metals. We can see that in how the composition of aeroplanes has changed over time. In 1969, the 747 was roughly about 80% aluminum. And we can see as time has progressed, in 2011, the 787 was roughly half manufactured out of composites by weight. Of the three main categories, metals are characterized by very good electrical and thermal conductivity. We see those characteristics exploited in electrical conductors for electric motors and in engine components, where not only strength but also thermal conductivity to remove heat from the heat engine is important. They are strong and stiff, and we can see those applications in the form of structural members, and here a frame for a camera. They have medium temperature resistance and are generally impact resistant. The other main category of ceramics, which includes glasses and glass ceramics, are formed from inorganic compounds. They generally do not conduct electricity, are strong and hard, which makes them brittle, and they can withstand high temperatures. These characteristics make them very hard to shape. We can see some applications here of some ceramic materials. We have naturally occurring diamond, which can be used to make cutting tools, such as drills. Here, the a sapphire crystal is used as a watch glass because it is highly scratch resistant. This furnace is lined with a ceramic refractory. Polymers are formed from organic molecules. They tend to have low density and a good strength to weight ratio. They're resistant to impact, hence tough. They're easy to form, and often polymers are called plastic for that reason. Then they are good electrical and thermal insulators. They're also chemically resistant. We can see applications. For instance, the fact that they are chemically resistant makes them good for packaging and piping. Their thermally and electrical insulating properties are exploited in this spray foam and also these electrical insulators covering the copper cables. Their toughness is useful for use in glasses and elastomer. This is an application of an elastomer to create a boot. So when we combine two or more materials, we can result in a material that has a superior performance to either one. Example though, those are concrete, which is a ceramic composite, carbon fiber, which is a polymer ceramic composite, and we have carbon-carbon polymers here. Carbon-carbon composites being used here in a high-performance brake rotor. Many natural materials are composites. For instance, bone is a ceramic polymer matrix, where the ceramic is hydroxyapatite and the polymer is collagen. Wood is a polymer-polymer composite formed of hard, strong cellulose encased in lignin. And shells are an example of a ceramic polymer matrix. There are some materials that don't neatly fit into the three categories that we have just mentioned. One of those advanced materials, such as semiconductors, used for computer chips. They have very interesting electrical properties. And nanomaterials, when materials are fabricated to a very small size, and nanomaterials encompass the range from 1 to 100 nanometers, they can have special properties. For instance, in I believe it's titanium oxide particles in sunscreen, when they're made a nano size, they are particularly effective. Previously, we classified materials by their composition and structure, but it's also possible or useful to classify them by their function. And so here we see some functional areas such as aerospace, biomedical, electronic materials, energy technology environment, magnetic materials, optical, smart materials, and structural. When we want to select a material for an application, some considerations should be the mechanical and physical properties that relate to the required performance, the ease of manufacture, the cost, obviously, of the raw material affects the economics of the final product, the aesthetics, availability, ecological and toxicological considerations. It's thermal resistance, expansion, conduction, corrosion resistance and compatibility with the operating environment, and its ability to withstand vibration and cyclical loading. Due to the large number of options of available materials, systematic methods have been developed to allow material selection. One of these is based on material indices or indexes. The way it works is we will plot relevant properties of materials against each other from a database. In this example, I'm plotting strength, which is the yield stress of the material, or related to the yield stress of the material, against density. The scales are log-log. There are lines drawn on the diagram, and these show lines of constant material index. So what do I mean by a materials index? We can do a mechanical engineering analysis of our situation to determine what particular ratios of material properties we want to maximize. In this case, we want to design a tie. A tie is a member in tension. If the length of the tie is fixed by our design, and as is the load that it will experience, then what we want to do, we want to change the cross-sectional area. The cross-sectional area will have to be large enough when such that the material will not permanently deform under the load F. To determine the required area, we need to know the yield stress of the material. The yield stress is the ratio of the force to the area above which the material will permanently deform. So we know that the density of the material is mass over volume, and the volume is going to be length times area. Therefore, the mass of the component is equal to the density times volume, which is equal to rho AL. We can eliminate A from the first and second equations to give us mass is equal to rho over sigma y F times L. We can see the mass of the component will be reduced if we use a stronger material. And obviously, it will be reduced if we reduce the density of the material used. Rho over sigma y is a part of this expression that is dependent only on the material chosen for the application. As we want to maximize or minimize mass, we want to maximize the ratio of sigma y over rho. This ratio here is called the material index for our application. Once we know what the material index is, we can use this plot. Here we have some guidelines. The guidelines show lines along which the material index indicated is constant. Here we have 3 material indexes shown. The material index will depend upon the situation, and a mechanical engineering analysis will determine which material index is important. In our application, we see that simply sigma over rho is the material index. If we draw a line parallel to the appropriate guideline, for example, this line here, then all points on this line will have a constant value of sigma over rho. In other words, their performance will be identical. As we draw our parallel line, or line that is parallel to the original guideline, further away from that line, so that's up towards in this case, it's going to be going towards the left and upwards, the ratio of sigma over rho for that along that line will be higher. So we have increasing sigma over rho, in other words, increasing performance. We see that the highest performance is going to be, or the highest values of sigma over rho is going to be achieved by using a composite material. If, for instance, we find that, say, for instance here, a rigid polymer foam in this section gives us an acceptable value, then we can look for alternatives that have an equal value of sigma over rho by just going along this line. So, and materials that are above and to the left of the line will exceed that value will exceed the performance of materials along that line. So in this way, we can identify candidate materials using this technique, and then this would be linked to a database allowing interactive exploration of possible materials. In material science, what we understand is that the structure of material is interrelated and dependent upon the processing, which is interrelated and dependent upon the properties that the material has, and hence its performance. So all these are interrelated. So for example, let's say we want to make a wood chisel. A wood chisel has some competing requirements in terms of the part of the chisel. We want the blade to be quite tough, so when we hammer on the chisel, the blade will not snap. However, we need a cutting edge that will remain keen, so that needs to be hard. How can we obtain these different properties? We could use different processing to get different structures to give us different properties from the same material. So for example, if we wanted to make that chisel, we would make it from a material, a uniform material, a uniform steel, or with a carbon content that is appropriate for the hardness that we want to get at the end. If we know the carbon content of the steel, we can then determine at what temperatures we need to heat it up to get it into a state where we can actually forge it. The same phase diagram here also explains how high we need to heat it so we get it into a single phase. And here what we're trying to do is we want to create the keen edge, and we do that by quenching it, cooling it quickly, heating it up above a certain point and then cooling it quickly. This results in a hard edge but yet retains a tough blade. So we can see here that even though the composition of the material is uniform, by processing different parts of it differently, we get a different structure, which gives us different properties, and of course, gives us the performance that we want. Issues in material use arise from the environmental impact of the manufacture of the raw material, manufacture of the product, packaging and distribution during its use, and then finally at its end of life. And this is called considering the product life cycle. When we choose materials, we want to be cognizant of the total impact, which is a measure of that is measured by the amount of CO2 produced. So for example, in this electric kettle, we can deconstruct the design choices for the materials and determine what the carbon footprint is for a particular batch of production. So we can see here for this kettle, the CO2 footprint from the materials and the manufacture is quite small compared to the transport. But the use of this kettle to boil water, which is energy intensive, accounts for most of the carbon footprint. In this case, we see the end of life potential is positive, has a positive CO2 footprint. So getting rid of the final device, it increases CO2. If the material was recyclable, highly recyclable, we may see this part showing a negative, hence offsetting the carbon footprint from the previous stages. You can see more examples of this on the link shown. Artificial intelligence impacts many disciplines, and in material science, artificial intelligence can be used to process the huge amounts of data and research on materials in order to determine what could be highly effective materials choices.